BJT in active region, because we studied BJT in different regions, active region, saturation, cutoff in general. So, but now we are focusing more on the active region, because in active region it acts as amplifier. That's why we are going to focus more on this particular region. First, we'll talk about load line. Why do we need a load line? Why it is called load line? Normally, load is kept at the output, because we drive, whatever we drive is called a load, and therefore it has to be located on the output characteristics. So why do we need actual load line? Without load line, you cannot have a direct relation between output voltage and output current. The direct relation between output voltage and output current is possible only when there is a load line comes into picture. So the load line is intersection of two plots defined as operating conditions. One is called DC load line, other is called AC load line. The intersection of those two is called load line. Let us see what exactly and how we have to make. First, I am going to talk about the necessity or the need of load line. For example, look at this characteristics, output characteristics. Suppose Vc equal to 1 volt. I have 4 ICs. Suppose IC equal to 1 milli, I have again 4 answers. Therefore, output characteristics cannot give direct relation between output voltage and output current. And hence we need a DC load line, which is a straight line on the output characteristics. So therefore, we have to draw the DC load line with the slope, and that's why we need it. For example, you take a circuit VCC, ICRC, VCE, IERE. Suppose there is a capacitor here. That capacitor is open circuit for DC. And now I am not bothered about input side. What is at input side we are not interested. You know why? Because we are only focusing on output side. In this current IC plus IB, I can neglect IB because IB is microamperes. If IB is microamperes, these two are almost in series. So let me apply KVL to output, then find out what equation is going to come. VCC minus ICRC minus VCE minus IC plus IB into RE, because this capacitor is open circuit. If you neglect IB, you will get IC as minus 1 by RC plus RE into VCE plus VCC by RC plus RE. Take this important equation. From here, suppose if VC is equal to 0, IC is VCC by RC plus RE. And suppose IC equal to 0, VCC is VCE. With these two, I can draw a straight line. This is called two intersects. And you know, this is one intercept for x-axis, another intercept for y-axis. So VCC by RC plus RE, this is VCC. And generally we take the center point as a Q point. That's called VCQ, ICQ. Now look at the point here. When you look at this point, this is Q point. Now let me ask the same question which we failed in without DC load line. Now this is DC load line. The slope is minus 1 by RC plus RE. Now suppose VC equal to 1 volt, IC is fixed value. For a IC given, VC is fixed. That's why this DC load line can give direct relation between output voltage and output current. By the way, why should we know the direct relation? In other words, at this voltage, this much current, how much current is coming? Why should we know that? Because most of the loads are operated not only in terms of voltage, but also in terms of current. For example, take the tube light. Tube light works at 230 volts and the current is known. Suppose 230 is given and the current is not given, that cannot go. Similarly, any load has a voltage rating as well as a current rating. So keeping these two ratings, and you can really see whether a particular load can be driven or not. That's the meaning we have here. That's why we are very much interested on the DC load line. And if the Q point is one of the values of DC load line, therefore Q point always vary on DC load line. So let me talk to you second with that idea, the DC load line. It's a straight line that passes through Q point with a DC slope, where CE is open circuit because for DC, capacitor is open circuit. Then third point is quiescent point or a Q point, an operating point. The word quiescent means sleeping. Sleeping means absence of AC. Absence of AC is nothing but DC. So Q point is more of a DC value than AC value. But AC signal is operated through that, therefore it is also called operating point. So Q is VCE comma IC, it is a specified value. And now look at this AC load line, and both are intersecting here and the signal is passing through that. So this is a DC load line, and blue is a DC load line and green is a AC load line. Now what is AC load line? It is also a straight line that passes through origin but with a AC slope. What is AC slope? Actually DC slope minus 1 by RC plus RE. Now RE is shorted. You know why RE is shorted? Because capacitor is shorted. Therefore AC slope is less than the DC slope, and hence if you see this, the slope is lesser. We can always draw any straight line with two things. From your childhood you know that straight line means two things required. 2 points are required, or 1 point and a slope. So while drawing the DC load line we have 2 points, but while drawing the AC load line we have a slope, and the second point is Q point. Fifth one, procedure for calculating Q point. So because how to calculate Q point? See, apply Thevenin's at input if required. You know why I have written this word called if required? Whenever there is a potential divider at input, you need Thevenin's. If there is no potential divider, you don't need it. That's why I said the word called if required. Step 2, apply input KVL. Step 3, substitute VB active 0.7 for germanium, 0.2 silicon, and get IB, and then IC is equal to beta times of IB. Please understand, IC equal to beta times of IB is valid only in active region. That's why today we are completely talking on active region. Therefore, I don't need to say again and again that IC is equal to beta times of IB. It is always valid in active region, because only in active region there is gain. Then go to KVL to the output, and step 5, substitute IC and IB and then solve for VC. The value of VC and IC is called Q point. Sixth one, location of Q point. So my fifth discussion is how to locate. Now it is where to locate. Where to locate the Q point? For example, this is PC max region. Output characteristic I took. Q point is taken well below the PC max region, because if you go to the PC max region, transistor is immediately burnt. By the way, what it means by PC? PC means maximum power, collector. How much power is to be dissipated, how much power is collected, and if that is maximum, the transistor is out. That's why Q point should be taken well below the PC max curve. Second point is operating curve for different PC. How to take the operating values? Take 0.2, VC by 2. You know what I mean is, you must avoid thermal runaway. If you take from 0.2, which is actually active point. So active region starts actually from 0, but practically from 0.2 to VCC by 2, that is called the active thermal instability. So please remember, this total is active region, this is VCC, this is VCC by 2, this is thermal runaway. Thermal runaway is very dangerous, and if you take less than VC by 2, you are a little more safe, but this is also unstable. So please remember 3 points. If you put the Q point here, it is immediately burnt. If you are put here, it is slowly burnt, but here this will also unstable. But the good news is thermal instability can be stabilized. We can stabilize this. It's possible. That's the good news. Otherwise, there's nothing that you can do in a transistor. Third point, VB should be greater than 0.7 for silicon and 0.2 for germanium because that ensures active region at the input. And VC less than or equal to VC by 2 is to avoid thermal runaway. So make sure you are active region and make sure that you are avoiding thermal runaway. And avoiding thermal runaway is not sufficient. You should ensure the stability. Stability is ensured only when IC is greater than VC by 2 times of RC plus RE. And after all that, we have a small thing to say. VC should be greater than 1 volt for silicon and 0.5 volts for germanium. Why? To make the collector potential a little larger. If collector potential is more, it can easily collect the carriers from emitter. And last point. Small signal current, collector current should be less than or equal to 0 signal collector current to avoid clipping. Suppose if AC value is more than the DC value, I will show it here. Look at here. Suppose this is AC value and DC value is here. Because AC is less, there is no clipping. Suppose AC comes down here, there will be clipping. So to avoid the clipping, you need to say AC value is less than DC. That's about how to operate. And never choose Q point in breakdown region. So these are the necessary things where to operate and how to operate transistor in active region. So let me illustrate certain things along with what you call to illustrative examples that will really give you much more clarity that all what I spoke. Let me take you to illustrative examples. Problem 1. Calculate Q point for the circuit VBB 2 volts, RB 100 kilo, RC 10 kilo, VCC 12, silicon with beta 50. I call this as 2 battery circuit. And if you apply input KVL, VBB minus IBRB minus VB is 0. From there you can calculate IB. And IC is beta times of IB. It is valid because active region. And if you apply output KVL, VCC minus ICRC minus VC is 0. From there you can calculate VCC as 5.5 and these are the values that we get. This is the Q point, how we calculate. In this process, understand first IB comes. So IB is also called quiescent value, but it is not called quiescent point. VB is also called quiescent value but not quiescent point. So when they say quiescent point, all these 4 values are called quiescent values. IB, VBE, IC, VC all are called quiescent values. But only VC and IC is called quiescent point. Problem 2. Calculate Q point for the circuit VCC 12, RB 100, RC and the same parameters but the values are here but the circuit is different. Input KVL, VCC minus IBRB minus VB is 0, calculate IB there and IC comes beta times of IB, VCC minus ICRC minus VCE, from there you will get the values of VCE. So this is the input KVL and then output KVL. This is how you have to calculate the values here. Okay. Third question. Calculate Q point for the circuit. This is also same circuit but a resistor is added here and you see how I am going to take it. VCC minus IBRB minus VBE, VCC, IC plus IB into R is equal to 0. From there IB comes and then IC also come and output KVL VCC minus ICRC VCE minus IC plus IB times of RE. From here VC will come because you will be substituting for IC and IB, then Q point will come. 4. In the circuit shown, IE is given as 2 milliamperes, V is given as 12, VCC also given as 12, RL is 5 kilo, calculate RE, IC, ICRL and VCB. So when you look at this circuit, RE is approximately VE by IE. So they already gave it as 12 by 2, 6 kilo. And you know IB is neglected, IC is approximately IE, that is also 2 milli. Now what is the value of ICRL? He gave IE as, IC as 2 milli, this is kilo. Kilo and milli cancel, therefore 10. So VCB is 12 minus 10 is 2. That's how we can calculate any values they are asking for. Question number 5. A silicon transistor is used in circuit shown in figure. If VBB is 4 volts and IB is 50 micro, calculate VB of 0, VB 0.7, determine RB for VBB4. Suppose if VBB is 12, how does they get effect? Circuit is very simple circuit. We only want to see for different values of VBE. If VBE 0.7, this is the value. VBE is 0, in the place of VBB, you should put 0 there and you'll get the value. And this is 0.7 there, you'll get the value, 0, you get this. So for different values of IB, you are going to get the values of RB. A silicon transistor with VBE sat 0.8, problem number 6. Beta RHF is 100, VC sat is 0.2. Is used in the circuit shown. Find the minimum value of RC for which the transistor remains in saturation. This is RC to be calculated, RB, and 6 here. When you take the KVL to input, 6 minus 200 kilo into IB minus VB sat is 0. VB sat is 0.8 because it is saturation. Solve for IB. And if you go to output, you will solve for another IB. And what is the relation between them? Output will give you the minimum required IB. Input will give you IB. If it is more than, if the input is more than output, you will calculate RC minimum. And if RC minimum is coming to be 3.7 kilo. Problem 7. For the circuit shown, beta is equal to 50. Find if the transistor is in cutoff or saturation or active, and then find V0. Find the minimum value for the emitter resistance RE for which the transistor operates in active region. Now look at here. This is a PNP transistor. N is given to N forward and P and P. P is given to negative. So we need to check where it is working. Actually it is reverse bias, but the value of potential will tell us. So assume that the transistor is in active region. Substitute input voltage minus drop 0.7 minus this. Then IC equal beta times IB because I assumed active region. IB is minus 73 micro, IC is beta times of IB 7.3 milli. So having got it, then go for output KVL, substitute. Finally, if VCB is positive given to P is forward. Output is forward and input was already forward. Therefore, transistor is in saturation region. Then the next problem is to calculate V0. And V0, if you apply output KVL, you can calculate that as 2 volts. Then for KVL at input, by assuming the values, you can apply the input KVL and you can solve for RE and RC minimum will come. So this is the meaning of the values that you can have. So emitter resistance you can estimate from the given values. Because anything less than or equal, but if we take equal, we call it as minimum. There is it. Problem number 8. If the transistor has high value of beta and VBE 0.65 and the current flowing through 2 kilo resistor will be. It's a very funny thing and it's a very popular question coming in the examinations. Here the beta value is not mentioned. He only says beta is very high. It's given in GATE exam and 2 marks, a very big question, is it? If you look at this, when beta is very high, what happens is, what is beta? Beta is IC by IB. If beta is very high, IB is almost 0. By nature, IB is small. When IB is small, what will happen? Neglect. But now he says beta is very, very high, then it is 0. Suppose if base current is 0 and this is 0, all these things are in series. All these things are in series. Now what to do here? Therefore, what will happen if very simply, this current will be 1 milliampere. That's a 1 milliampere current because IB1 is 0, IB2 is 0, they are in series. So why 1 6.5 plus 1.85 plus 1.65 is 10. 10 into IA is equal to 10 volts, therefore 1 ampere. Then this I will come here because this is 0, this comes down. Again IB is 0, this comes down. So what he is asking is here, but we are going to calculate here. Now please apply KVL here. He said 1.65 into IA, that means 1 milli, kilo and milli cancel, 1.65 minus 0.65 is equal to this drop. And what is this value here? Very simply, I is equal to 1 milli. So without calculating anything on the output, I have jumped from here to here simply because base current is 0. This became a very fantastic idea as far as beta is very high. You know, when beta is very high, the design is becoming independent of the device. In engineering, one of the greatest achievements is the moment the design is independent of the device, you are going to achieve a greater thing. You know what's it? Even there is a change in the parameters of the device, it's not going to affect because independent of the device. And even if you change one device to another device, it's not going to affect. So design independent of device is the greatest achievement of an engineering in any field of engineering, not only in electronics, even in mechanical. So the moment, even in day-to-day life, suppose some system is created independent of a person and the system will be stable. Suppose if you create a person depending on one person, if that person leaves the organization, system becomes unstable. So every system and every design should be made independent of the device. And that's possible only when beta is very high. And that's a very good challenge here to design such circuits where beta is very high. Therefore, when beta is very high, if you put one transistor or another transistor, the design will work. Even within the same transistor, if beta is changing with temperature, design will work. What a beautiful idea to say beta is very high. Another interesting thing I am telling you, if beta is very high, you know what's going to happen? BJT will almost behave like FET and op-amp. Because in FET and op-amp, anyway input current is 0. Here, if beta is very high means IB is 0. It will behave just like a FET. That's a good approach. That's a good idea about BJT having beta very, very high. Now let me take you to the 9th problem. In the circuit shown in figure, VCC is 26, RC 20 kilo, RE is 470. If a silicon transistor is used with beta 45 and if under quiescent conditions VC is 8 volts, calculate R. We need to calculate this. And please understand here, this is IC, this is IB, therefore current in this element will be IC plus IB. So VCC minus IC plus IB into RC minus VCE minus RE into IC plus IB is equal to 0. That's input KVL. From there you can estimate and say beta IC equal to beta times of IB, and the only unknown becomes IB, and solve for IB there. Once IB comes, IC will automatically come as beta times of IB. Therefore IC is this much, 860.2 micro. So because when you have a big loops, you will definitely confuse saying one thing. Wherever VBE comes into picture, it's called input KVL. So first you can take output KVL, then you can take input KVL. From output KVL, you can calculate IB and IC. You know why did I take output KVL? Look at your circuit here. Here in this output you know everything. So you know VCC, you know VCC is given, RC is given, VC given, everything is given. Therefore you can just calculate IC. By calculating IC, you can estimate R. So generally for every problem we go from input to the output. For this problem we go from output to the input. So that's the idea that I want to show in this problem, and enjoy this and really say how to calculate the value of R. And last problem, calculate the values of the 3 currents in the circuit. 3 currents means IB, IC and IE. It's a very simple sign. So here is it. You can say VCC minus 1 mega, VBE, IC plus IB into 1 kilo. You will get here. Then VCC minus IC into 2 kilo minus VCE minus IC plus IE. The point is, he is not asking for VCE. Simply what you can do is apply input KVL and solve for IB. Once IB comes, IC comes, and IE is approximately IC there. Let's go to worked out examples. Worked out example 1. For a BJT, common base current gain alpha and the collector base junction reverse voltage IC naught. This BJT is connected in common emitter mode, operated in active region with base driving current IB. The collector current for this mode of operation is very simple. This is collector current is generally IC equal to beta times of IB plus 1 plus beta times of IC naught. Very small problems are given. That's why my illustrative examples are always tougher than the workout examples. I mean, the examples that I have taken is always tougher than the examples are asked in the question papers. Option is D. The quiescent collector current IC of a transistor is increased by changing resistance. As a result, GM will not be affected, GM will be decreasing, GM will increase or decrease depending upon the bias stability. This is the second problem. Question number 2. What is GM? GM is generally given by IC by VT. GM is directly proportional to IC. If IC increase, then GM should also increase. Therefore, option is C. If IC increase, this is also increase. Question number 3. In the amplifier circuit shown in figure, the values of R1 and R2 are such that the transistor is operated such that 3 volts and IC is 1.5 milli when the beta is 150. The transistor with the beta 200, the operating point. He is trying to change the values of beta here. For different values of beta, how does the circuit get affect? The Q point with 150 is given and he is asking Q point with 200. What will happen? So VCC IC, you can take common, and VC, from there you estimate R2 value 2 kilo, and IC is beta times of IB, therefore IB is 1.5 by 150 because beta is that much. If beta is 200, now IC will become increased, then VCE will become 2. So therefore, the option is 2 milliamperes and 2 volts. That's what you are going to get. Option is A. Problem 4. Assume VC is at 0.2 and beta is 50. The minimum base resistance, base current is IB, required to drive the transistor into saturation. That's a very simple, a very interesting, what's the condition available here. Suppose, take the output KVL here. You have a minus VCC output I am taking, and I am going to apply from here. If I go in the reverse direction, IC will become 2.8 milli. Therefore, beta times of IB 2.8 by 50. IC is 56 micro here. IB value is 50 microampere here. That's the option that we get for this problem. Problem 5. Assume that the beta value of a transistor is extremely large. Once again, the value came extremely large. VB is 0.7, IC and VC in the circuit we should calculate. Solution. As I told you already, whenever beta is extremely high, IB is very small, neglected. Therefore, V Thevenins you calculate VCC by R1 plus R2 into R2. That becomes 1 volt. R Thevenins, of course, you don't need to have R Thevenins because base current is anyway 0. So if this is 1 volt, this is anyway neglected. 1 volt minus VBE minus 300 into IC plus IB, you will get IB from here. Once you get IB, IC is beta times of IB, you will get IC there. In the process, actually IB is already neglected. So this is 1 minus 0.7, 300 into IC. So IC will directly come. IC is equal to 0.3 by 300, that becomes 1 milliampere. And once the output KVL you take it, VCC minus 2.2 IC minus VCE, IC into 300, you will get VCE as 2.5. So whenever beta is high, the only good advantage you have is IC becomes IE because IB is 0, and R Thevenin is also not required because the drop across R Thevenin is also 0. That's why the option is C. Problem 6. For the BJT circuit shown, assume that the beta value of transistor is very, very high. Again, the value of beta value is coming, and VB is 0.7, and the mode of operation we need to check. Is it cutoff or saturation or normal mode or reverse active mode? Normal mode means normal active mode. Reverse active mode means invert mode. So he has given these values. Please understand, appreciate the value of beta is very, very high, as I already told you. If beta is very high, IB is 0, then consider this value, calculate IC, then consider. So what is the meaning here? The value required from the only thing that you need to check is IC active should be greater than IC sat. Therefore, BJT is in saturation region. Option is B. Option is B. Problem 7. A circuit using BJT is shown in the below figure. The value of beta we need to calculate because he gave all other options. All that he wanted to check for us is the value of beta. And look at here, VCC minus VE minus 4 is equal to IE into 10K. Even here also you can have it. From there, IE is coming as 1.66. IB is VB by 100 kilo. This is 100 kilo. And please understand, this is emitter. Emitter is given 10 volts. This is a PNP transistor. IC is beta times of IB, IE is IC plus IB. So if you calculate IE as beta plus 1 times of IB, therefore IE value you can, beta value you can estimate as IE by IB. If you calculate IE by IB, beta will become as 165 because 1 plus beta comes to 166, therefore beta is 165. Option is C. Problem 8. For the circuit shown in below, by assuming beta 200, VBE 0.7, the best approximation for the collector current in the active region. First of all, check it. NPN transistor, forward, reverse, active region. Then calculate the value of IC. Very simple. Generally, we go for input KVL. In the input KVL, we will be estimating IB, and where we will say IE is equal to IC plus IB, and everything converted back into IB. Estimate IB, and then IC comes there. Then IC value you can estimate as 1 milliampere. So I am taken input KVL. From the input KVL, we can get IC. Therefore, option is A. Ninth problem. In the transistor circuit shown in below, the collector to ground voltage is 20. The possible condition is, what is the possible condition? Collector emitter terminal shorted, emitter to ground connection open. 10 kilo ohms resistor is open. Collector base terminal is shorted. So what is happening here? This is input is given, output voltage also given. We need to check how is the biasing. From output KVL, you can say this 20 minus this is equal to VC there. VC has got one equation. From there you can say VC is equal to 20 if IC is 0. And if it is possible only if IB is equal to IE is equal to 0, for this emitter must be open circuit. Therefore, the option is B, open circuit. Option is B. 10th. In the below circuit as shown in figure, beta is 99, VB is 0.6. Then what are the values of VC and IC corresponding to the operating point? He is simply calculating. Please remember, whenever you have a resistance from collector to base, you will have IC plus IB here. So I will take input KVL and output KVL. VCC minus IC plus IB minus IB RB minus VB is equal to 0, and that's the input KVL. Substitute everything and get the value of IC there. Once IC come, then go for output KVL. VCC minus VC is equal to 2.5 into IC plus IB. You know why this 2.7 came? Because as I told you, the current in this drop is IC plus IB. And that became 4.67. The value is A. So we have the option as A. So this is how we can solve the problems of transistor. And I have given the illustrative examples and also previous questions there.